Hello, this is the solutions to sample exam 3 for Math 2414 Calculus 2 on sequences and series. So some of these problems at the beginning should fly through pretty quickly. I'm sure your issues probably are more toward the end. Let's see what we have here. Write the first 5 terms of the sequence. Formula is given by an equals n minus 2 over n squared plus 1. Beginning with 1, just plug in 1, 2, 3, 4, 5. I don't have the answer here, but the answer is on the key. So hopefully that one didn't cause you too much trouble. Should be an easy one there. Now what I don't have on here is a recursive problem. So there's a chance that might be on the test where you find a certain term of a recursive sequence. So go back and look at my notes for that. It's not too difficult. That just means you use a previous term of another sequence to calculate the next term. All right, next problem is find the fourth term of the sequence. So all you got to do is plug in 4 for n, like I did here, negative 1 to the 4 plus 1. That's going to make it negative. 2 to the 4, and then over 3 times 4 minus 1, and you'll get negative 16 over 11. Now the third one, come up with a formula for this. The numerator is pretty easy, 1, 2, 3, 4. That's just pretty much n if you're starting with 1. Now the bottom, you see 4, 9, 16, 25. Those are squares, obviously. But you wouldn't start with n squared. You have to, because if it was started with n squared, it would be 1 over 1 would be the first term. So it's just adjusted by 1. So it's n plus 1 squared. So that way you have 1 plus 1, 2 squared is 4, 2 plus 1, 3 squared is 9, so forth, so on. All right. Number 4, simplify. Okay, it's pretty easy to simplify the 2's. Using property of exponents, 2 to the n plus 1 would be 2 to the n times 2 to the 1. So the 2 to the n's would cancel, leaving 2 to the 1 on top. Factorials, you start with the largest factorial of the 2, whether it's top or bottom. In this case, it's the bottom, n plus 1. So n plus 1 factorial would be the same as n plus 1 times n factorial. So you stop when the factorials match. Then you cancel, so you would just be left with 2 over n plus 1. Now, looking at problems involving whether or not a sequence converges. Now, the sequence converging always means as n goes to infinity. Obviously, in the world of limits, you can find limits as they approach any particular value. But this is implied as n goes to infinity. There's no other situation here. So if it says, like number 5 says, find the limit, well, that's always the limit as n goes to infinity. Now, number 5, okay, it's pretty easy. If you don't have to use Hopital's rule on that. If you just realize that you have a larger power on bottom than the top, as that goes to infinity, that's going to be 0. So it converges to 0. Now here's another one, involves simplifying factorials. And n over n minus 2 factorial, number 6. So you start with the larger of the 2. Come over here, see that's the, started with n factorial, because n's larger than n minus 2. So you go n times n minus 1. You have n minus 2 factorials, both cancel. And then you have n's left on top, and that will go to infinity. In fact, I'll give you a little hint on these kind of problems where it's just factorials, like this one was, and not some other terms in there, just factorials. The answer for the limit can only be one of 2 things. It's either going to be like this one where it diverges. I didn't write diverges. Infinity means diverges, so it would be that answer right there. But the only possible other answer can be is converges to 0. There's no other possible answer. Because what happens is either the ends are left on top, like this problem was, or the ends end up on bottom, meaning you have 1 over some ends, and that's going to go to 0. Number 7. Let's see what we have here. We have pretty easy, whether you do Hopital's rule or if you just compare the 2n over the 3n, and they have the same n as the same power, so it's just going to be 2/3. I showed Hopital's here, but you did not have to do Hopital's. You can kind of look at it and see that it's going to go to 2/3 and then goes to infinity. Number 8. Let's see, that's one of these ones where you have the indeterminate forms and you have to use that log rule where you bring the limit down. And so what I did, I took n plus 1 over n, I rewrote it, just broke it up into 2 fractions, made it 1 plus 1n raised to the n, which that's famously already, we saw that in the notes. In 8.7, Hopital's rule, it ends up being e, so you can actually see it done there also. But this is the deal where you have to give it some sort of variable name on the other side, and then you apply logarithm to it. And so you log it, brings the n down, and then you have the limit of n times log of 1 plus 1 over n, and you have to get it into a fractional form to use Hopital's rule. One thing you should never do is when you're deciding which one of the two things to drop is don't ever drop ln to the bottom. So you leave the ln where it is, and you write n as 1 over n, because multiplying by n is the same thing as dividing by 1 over n. They're equivalent. So now I come over here and I do Hopital's rule. Now the derivative of natural log is basically du over u, so it's 1 plus 1 over n prime over 1 plus 1 over n. And then the bottom I just wrote 1 over n prime. And I cancel those two terms out. You might be looking at that, well, wait a minute, those aren't two terms are equal to each other. That's true. But what we're canceling out is that their derivatives would be equal. The derivative of 1 plus 1 over n would be the same as the derivative of just 1 over n, because the derivative of 1 is 0. So it cancels and leaves a 1, and then as n goes to infinity, 1 plus 1 over n would be 1 plus 0, 1 over 1 would be 1. But remember, the final answer is, because that was ln of y, so the final answer is always y equals e to whatever you get in this step right here. So it's not, the answer is not 1, it's e to the 1, or just e. So it converges to e. Number 9, geometric series. Always pay attention to where the counter starts for these geometric series. Be real careful, because the formula that I have provided for you, a over 1 minus r, is implying that n starts at 0. Now, the way I did this in my notes, and I actually learned another way to do this later on, I'll just tell you that one verbally, but this is perfectly correct what I've done here, is if you use the a over 1 minus r, 3 over 1 minus 0.6, and then subtract off the term before it, which is the 0 term. So, if because the formula is giving you 0 through infinity, but we only want 1 through infinity, so we have to use the formula and then minus off the term that we don't want, which is n equals 0. Ends up being 3 times negative 0.6 to the 0. And work all that out, use your calculator, blah, blah, blah. You get negative 9 over 8. Just answer A here. And the other method is, you could have just brought out a negative, when it starts at 1 like this, just bring out a negative 0.6, and that would be 3 times negative 0.6, which is negative 1.8. That would be your new a, and then you can use a over 1 minus r. Now, I promise you that'll be the exact same answer. So that also works. So you can do that if you like. Number 10. Now this one's geometric, e over pi. Those are both numbers. And first we have to decide if it's converging geometric or not. That's what I forgot to mention in the last problem. But if I'm asking you to find the sum, I'm sure it'll be converging. Versus asking you, if it converges or not. Now e over pi actually is less than 1, so it would converge. So that means it will have a sum. And it starts at 0, so we just have a, which is 1, because there's nothing there. 1 over 1 minus e over pi. So just to make it match that answer, which you could obviously use your calculator and just get the decimal equivalent. You can do it that way too, but it wasn't too hard. Just take that 1, make it pi over pi, and get a common denominator and flip that bottom pi over, and you have pi over pi minus e. Now the next one's talking about what would convergence, divergence of the following series. State the test used. Now this is 1 over 3 to the n. We'll jump down to the n for a second. But we always want to pay attention to, what all ways it would converge. And 1 over 3 to the n is exactly saying the same thing as 1/3 all to the n. So yeah, the answer key says geometric, but also root test would work here. And you could probably even use integral test to work here. But anytime I want to use integral test, I'll make sure it's something where it would be pretty obvious that you would integrate it. Probably would not include integral test on the answers for this kind of problem. But root would work because it's all raised to the nth power. In fact, here's a little tidbit for you that only works one direction. Anything that converges by geometric will also converge by root, but not vice versa. Not all roots are geometric, but all geometrics are also roots. So that's whether it's converge or diverge, by the way. If it's diverging geometric, it would also be diverging root. Let's come down here and take a look at number 12. We have 1 over n minus 1 over n plus 1. That's a telescoping series. Telescoping series always converge. So I'll have a problem where you find the sum of the telescoping. And this one, and the rule of thumb on this is, and it also applies to number 15. So I'll use it again when we get to that one. But the quickest way to do this is, well, first you can list out some terms like this, and you can sort of see that some things are going to cancel, and eventually the remaining terms on the right will all eventually go to 0. They won't equal 0, but as a limit standpoint, they'll approach 0. And you're only left with this 1 right here on front. So in my notes, I mentioned a little trick there that if you look at the difference between n and n plus 1, which would be 1, that means it will be the first term in the first parentheses. So that's a little trick. So if it was a difference of 2, you would take the first term in the first parentheses, and then you would add it with the second term in the second parentheses. The first term in the second parentheses. It's always adding first terms. So what you could do then, let's say if you knew it was 2 of those, you can just generate those 2 terms and add them together without having to list out a bunch of stuff if you don't want to. But if you want to list them out, go ahead. Now, so that one just converges to 1. 13, what kind of test we could use here? Now this one should also say integral. So if integral was a choice, because you can integrate that. Because in section 8.1, that was a technique in my notes called the disguised form of the log rule. That means you would multiply top and bottom by e to the n, or you obviously can change these from n to x if you're integrating. but multiply top and bottom by e to the n, and then substitution works. And that'll be a diverging improper integral. But this also works too, because you take the nth term test and you put infinity with e to the negative n. E to the negative n as n goes to infinity would be 1 over e to the n, and that term by itself would go to 0. Not e to the positive n, that would go to infinity. But e to the negative n goes to 0. So then you just have 1 over 1 plus 0. So the fact that that limit goes to something other than 0, that's what the nth term diverges by the nth term test means. It means that if the limit goes to anything other than 0 of the sequence, the series will diverge by the nth term test. So 14, identify the type of series. It would be telescoping. I don't have any none of these answers. I might be changing this review for future generations anyway, but there's not any none of these on the test. You don't have to worry about that. They'll all have answers. I don't want to trick somebody with that. I want to make sure the answer's there so you can see it. And yeah, that's definitely going to be telescoping. Telescoping series. That's the name of the series. If you were actually testing this for convergence or divergence, telescoping series would work. But you'd also could, limit comparison test would also work as far as testing it. But the series itself is a telescoping. So is number 15. So number 15, you have to do a little simple partial fraction decomp. Not too difficult. If you have to do that in a test, it will definitely be a distinct linear. It'll be that first easy case. So it's not too hard to break this down. And you end up with 1/2 and negative 1/2. So we have, now I pulled out the 1/2, which is fine. Or you can just leave the 1/2 in the numerator of the individual fractions, your call. The thing about it is, if you pull the 1/2 out, don't forget to multiply what you have left by that same 1/2. So the little trick I was telling you earlier is the difference between n plus 1 and n plus 3 is 2. And so all you have to do is take the first term of the first parentheses and add it to the first term of the second parentheses. So that's how you know. Then it was 3, we'd go over to the 1/4. But that's really easy. You add those together, but this problem has that 1/2 out in front. So as long as you don't forget that, you're okay. So that one's going to converge to 5 over 12. Number 16, choose a series that diverges by the nth term for divergence. Let's see. Well, it's pretty much number 1, because that's going to go, number 1, A. That's going to go to A. And go to 1, which is not 0. The rest of them would go to 0. B is kind of weird with the factorial there, but the factorial would produce a lot of n's on the bottom, so it makes it go to 0. But the main thing is that A is obvious that that limit goes to 1, which is not 0, therefore that's the one that diverges by the nth term test. The rest of them will all go to 0. Now remember, you can't use the limit going to 0 as proof of convergence. It doesn't work that way. It only works that if the limit does not go to 0, then you have a diverging series by the nth term test. Number 17. Which series converge? A is a diverging harmonic series, also P series integral. B is no good because it's geometric and the R value is not between -1 and 1. C is no good because it's a diverging P series, just sort of like A is. And D is a converging P series because the exponent for n is greater than 1. So the answer is definitely D. All right. Now, number 18. which of the series diverges. 1 over 2 to the n is the same thing as 1/2 to the n. And the C, I'll jump over B for a minute. C is a converging p-series. I'm sorry, telescoping. D is a converging p-series, and there's none of these that you don't have to worry about. B would be it, because that limit does not go to 0. As I showed over here, what you have is just terms that are alternating back and forth as you change n. 3, 5, 3, 5, 3, 5, 3, 5. It's never going to approach anything. Not only not going to have any kind of limit, much less, so certainly not 0. So it definitely would be B. Number 19 is pretty much straight up p-series, diverging p-series, n to the 2/3. 2/3 less than 1. That's the criteria for p-series divergence. Number 20. In this set of answers, integral is the correct answer. It wouldn't be, obviously it's not geometric. It wouldn't be n-term test for divergence, because that limit would go to 0. You could do one Hopital step and see it goes to 0. It's not telescoping, integral. Direct comparison test would also work here, because you could say 1 over n, compare it to 1 over n. Limit comparison test would not work, but direct would. 1 over n, smaller diverges, means larger diverges. And ln of n over n would be larger, except for we're starting at 2, though. It wouldn't be at 2, because ln of 2 is actually smaller than 1. But once you get past 2, every other term would be larger than 1, so this entire series would be larger. All right, so I just want to mention that about the DCT test there. So 21 is a weird-looking problem, but the integral test would work perfectly on that. It's an excellent U substitution problem. I don't, let's see, I'm thinking, never thought about this before, but I think limit comparison test, this answer is kind of giving you, nothing but integral test answer choices, but I think limit comparison test would work here. Because just imagine if you put cosine of -9 over n in the numerator with n squared on bottom, you could compare it with 1 over n squared. No, I'm sorry, I said limit comparison test. I meant direct comparison test, excuse me. And for converging on the direct comparison test, it means larger converges means smaller converges. So 1 would always be greater than cosine of -9 over n, because cosine is always between -1 and 1, greater than or equal to. 1 would always be greater than or equal to. So yeah, I think direct comparison test would certainly be valid here. But definitely the integral test. The integral is not too bad. It looks weird or complicated, but it's just U substitution. You just let u equal -9 over x, and that gets you that 1 over x squared you need out here. So then it just turns out being cosine u du. Works perfectly. This is not a bad improper integral problem. Would be a bad one on a test to ask, because easy once you get the u sub part right. Okay, antiderivative of cosine of sine. I like to change my limits of integration. If you don't, be sure to change them back when you're done. And I got some weird looking answer, but it's a real number answer. 1/9 sine of 9. So the series does converge by the integral test. Like I said, also I can think it's safe to say direct comparison test convergence would also be right. Alrighty, so 22 is another integral test problem. And it would not take too long doing a basic U substitution to see that diverges, because you end up with that ln part that's going to go to infinity. So it diverges. 23. I have integral there. which is perfect. That's correct what I did. I'm also thinking now direct comparison test would absolutely be valid here, just like it was for ln of n over n. So direct comparison test would also work. Now I know it sort of sounds like it's not uncommon for an integral and a direct comparison test to work together, but that's not a rule or anything like that by any means. So I have the integral test worked out here, but I'm also going to throw a direct comparison test in there. You would compare it with 1 over n. Limit comparison test would not work for this one. 24. All right, so we have 6n squared over n cubed, and that's perfectly set up for a limit comparison test. It's very important that you compare it with the correct thing, because this kind of problem on a test, I like to put, obviously I'm making it obvious to use a limit comparison test, but I also make, not only do I change around converge and diverge, I also put what's the thing you have to compare it with. Like this has to be 1 over n, it has to be the difference, in the exponents. Sometimes I use fractional exponents. I think that was like a quiz problem. But anyway, yeah, you can compare it with 1 over n, and 1 over n is a diverging p-series, so therefore it means your series, if your limit's a finite positive number like this is with 6, and you can flip it over and you'll get 1 over 6, so either way, and that means your series you're testing will do exactly as the series you're comparing it with. So if the series you're comparing it with diverge, that means your series diverges by limit comparison test. Now here's one thing to mention is that limit comparison test and ratio test don't usually work together. In fact, ratio test does not ever work for these polynomial terms. I mean, over 99% of the time you would not have. Could be some exceptions. Not for the polynomials, I meant just in series in general. There could be some where the ratio test and the limit comparison test could work, but most of the time it's safe to assume that they're not going to work together. If you're having to make that kind of choice on a test, which if you're having to choose between two choices, which ones. So if you see ratio and limit comparison test together, I think you pretty much assume that's not going to be the right answer. 25, same thing. And actually you're comparing it with the same thing also, because you're kind of ignoring the 2 to the n here, so all you're focusing on is on this right here. So basically the cube root of n cubed is just n, so you're comparing it with 1 over n. So that's pretty much the same thing. We get diverges again. Now the next one's an LCT, but we compare with 1 over n squared right there, because n cubed over n to the 5th, we reduce to 1 over n squared. And so, but that's, the limit comes out to be 3 here, so we get a finite and positive number. But now 1 over n squared, instead of 1 over n squared is a converging p-series. Therefore, this series converges by the limit comparison test. So let's see what 27 says here. Sine of n over n cubed. This should be direct. Yeah, converges by DCT, direct comparison test. Yes, because sine of n over n cubed would always be less than or equal to 1 over n cubed. And direct comparison means larger converges, smaller converges. And larger definitely converges because it's a converging p-series, 1 over n cubed. So direct comparison test, that's about the only thing here. You really couldn't integrate this one, because if you bring that, you can integrate n cubed times sine to the n, but not n to the negative 3. That will not work. 28 is alternating series because it has that negative 1 in there. So you ignore the negative 1, you take the limit of 4 over 3n plus 1, goes to 0. and then the terms are supposed to be not increasing, so equal or something. That's usually an automatic. You see, I didn't really show anything there. I probably just did a couple terms in my head or whatever, but frankly, I've never noticed one that's failed the first part of the test and then not passed the second part. So now I think I have one of my notes or something here, but sometimes I guess you have to be careful. I don't think that's not going to concern you for test purposes or whatever, but in general, you can have maybe the first term or two doesn't apply that way, but then after, let me bring up a journal here and show you what I'm talking about. Let's say these are each terms. Let's say it does this. It might slightly increase temporarily, but then just start decreasing forever and ever, and after that, like that, start flattening out. So, if it was doing that, that would actually be okay. If the first couple, 3 terms are increasing, that's okay, as long as it shows steady decrease the rest of the way. And if you really wanted to prove it even further, you could use something from Calculus 1, about increasing and decreasing functions, and you could take the derivative of 4 over, you could use x if you want to, 4 over 3x plus 1, and you would see that derivative is going to be negative, so it's definitely, remember, negative. For all real numbers, it'll be negative. So that would imply it was, decreasing with a negative first derivative. Okie doke. Let's see, 29. Yeah, the absolute convergent, conditionally convergent, or diverges. Those will be the 3 answer choices for this kind of problem on a test. Once again, you won't have the none of these business like number 30 showing, but now there's different, my notes show a couple different ways to go about this, but if you want to check the alternating series test first, that's not a bad idea, because if you do it that way, at least, and you get diverges, and then the problem's over. You can stop. It's diverged. But if you get converges, then you have to go to the next step to determine whether it's absolute convergence or conditional convergence. Meaning you have to, so this one definitely passes. The limit of 1 over e to the n is n goes to infinity, goes to 0, terms are decreasing, so we have converging, so we've effectively eliminated diverge from the answers. Now we have to test it without the negative 1 to see if it converges or not. And this definitely does. It'd be the same thing as 1 over e to the n. I think this one was on the quiz also. Yeah, this one I have converging geometric, which is correct, but this one converges geometric, root, integral. I think even ratio test works on this one. In fact, when I said earlier that when, if geometric, then root applies, I believe that's also true that ratio applies. That should be right. Root, it's not always root and ratio both apply at the same time. That's certainly not true. But the ones that are geometric, I believe, are not only are they also root, they're definitely also ratio. But anyway, so what that means is that if it converges with the negative, like it did with the alternating series test, and it converges without the negative, you have absolute convergence. That's what we have here. Now, number 30, we have it converges by the alternating series test. So we've eliminated diverge. However, this one's a little tricky. Looks almost like integral or something, but this is another one with a direct comparison test. We would say that 1 over n is smaller than 1 over ln of n plus 1. Keep in mind that ln of n plus 1 is going to be greater than n, but then that makes the fraction, let's see, no, I'm sorry, I have that backwards. N is greater than ln of n plus 1. Excuse me, I have that backwards. So the ln of n plus 1 is a smaller denominator, which then makes the fraction larger. So, okay, I just said it wrong the first time, but this statement's correct right here. Smaller diverges means larger diverges. So that's what conditional convergence is. That means if you converge by the alternating series test, but then if you do it without the alternating series and it diverges, that means conditionally convergent. Because what that means is it's saying that the series converges on the condition that it's an alternating series test, meaning it had to have the -1 there. Unlike number 29 means it converges with or without the -1. But 30 had to have the -1 to converge. And that's what's called, that's what conditional convergence is. Let's take a look at 31. Converges by alternating series test. And then you want to do LCT here, and so you're reducing the square root of n over n. That's the same thing as reducing those powers as 1 over n to the 1/2. So it's important that you compare it to get those powers correct. And that's 1 over n to the 1/2 diverging p series, and that's going to work right here. So this is another one that's conditionally convergent, meaning that it only converges with the -1 there as the alternating series. Without the -1, doesn't converge. So that's conditional convergence. Now 32 is also alternating, but it fails the alternating series test because this limit with the, you don't have to do, the Hopital's rule here, but n squared over 3n squared pretty much means it's going to go to 1/3 as n goes to infinity. So fails alternating series test, problem's over. It diverges. All right, number 33. Okay, number 33 is just a straight up alternating series test. It's not asking for absolute or conditional here. Just so pretty easy to show that one converges by alternating series test. 34. That's going to be a ratio test. Only a ratio test. Not a root test, because even though it has that 3 to the n, you can't. The only way you can use the root test in this case would be is if there was if you had the entire thing wrapped in parentheses and raised to the nth power. So this is strictly only a ratio test. This is where you have to do the n+1 term right there. And so it's n factorial becomes n+1 factorial. 3 to the n becomes 3 to the n+1. And you're actually dividing by a to the n, but what I always did on my notes to make this a lot quicker is dividing by a to the n, which is the original series, multiply it by its reciprocal just to save you a step. So the first part's always replacing n with n+1. The second part is always the reciprocal of the original series. It just saves you a step, makes it a lot faster. And earlier on in the sequences part, earlier in the review, we saw the reducing of the factorial. So n+1 factorial would be n+1 factorial times n factorial, which would cancel that n factorial. You would be left with an n+1 on top. And then here you'd be left with a 3 on bottom, because it'd be 3 to the n times 3 to the 1. 3 to the n would cancel, leave 3 on bottom. And you have n+1 over 3, and that goes to infinity. So you have diverges by the ratio test. Actually, had you flipped this original series over here over, the other way around, flipped it upside down, you would have gotten 3 over n+1, which would have gone to 0, and you would have had converges by the ratio test. But this particular one diverges. The next one. So same thing, replace n with n+1. And then you multiply it by the reciprocal of the original series. Go from there. Now I didn't show, okay, I'm not displaying the 8 now. The 8 is going to be the same way that the 3 works. But this is kind of interesting because these do cancel. n+1 to the 8 over n to the 8. Not algebraically, but from a limit standpoint they cancel. In other words, if you expanded out that n+1 to the 8th power, you'd have quite a few terms. 9, I believe. But the largest would surely be n to the 8th. So if you look at n to the 8th, because remember that as you go to infinity, only the largest powered term applies when you're in a rational situation like that. So you could ignore all the smaller terms. So it's basically just n to the 8th over n to the 8th. And so that really does go to 1, even though it doesn't cancel algebraically. It's because of the limit as n goes to infinity. So you end up with 1 over 8, less than 1, converges by the ratio test. (36) n plus 1 over 3n plus 1, which could prove the divergence of this series. That would definitely be the nth term test, because the limit of that ends up being 1/3. Also, but it wasn't a choice here, also integral tests would work on this. Because one of the things we learned about partial fractions, or you can go back to stuff and with logarithms and stuff and integration in Cal 1 with because you could divide here. You could actually do division and then integrate. So I just want to mention the integral test does work, but out of those answer choices, it's definitely ignoring the none of these. It's definitely the nth term test. But you could divide and then integrate. That would work too. Nothing else does though. 37 n factorial over e to the n would be ratio test. Usually factorials are going to be ratio test. That's one way to tell. But we had this one, our weird stuff mixed together. Like the n to the 8th over 8 to the n. That's not geometric because of the n to the 8th. So ratio test. Ratio test here. You have n plus 1 factorial over e to the n plus 1. Multiply it by the reciprocal of the original. You'll get e on bottom, you'll get n plus 1 on top, and that's going to go to infinity. So you have diverges by the ratio test. 38, that's definitely a root test. When you see everything in there, even though earlier I said all geometrics are roots, I mean, when I say root test, this is exclusively a root test. It's not geometric. So the root test is actually pretty easy. You're just taking the nth root of that, which kills the exponent n. So all you're evaluating is the limit of what's on the n side. And if that's less than 1, you're the positive aspect. Well, this doesn't have negatives, so we would, absolute value kind of, technically the rule has an absolute value in it to eliminate any alternating series negative stuff, but that won't be an issue for you to have to worry about. So if you take the limit of the inside part, that's real easy to see that this is 2/5. Just eyeballing it or doing one with Hopital's rule. 2/5 is less than 1. Converges by the root test. 39, choose a series that converges. A definitely does not. We've seen this one earlier. That fails by the nth, diverges by nth term test. C is a failing geometric. D is a P-series divergence. Ignore the none of these. So it has to be B, and what you would do for B would be the ratio test. I didn't work it out here. Obviously, it has to be the answer, but if you wanted to work it out for practice, you would then see that it converges. In fact, I can tell just by eyeballing it, you're going to end up with 2 over n plus 1, which that limit will go to, as n goes to infinity, will go to 0. So you absolutely have converges by the ratio test. So 40. Taylor polynomial, pretty much plug and chug on this. Let's see, I don't have the formula sitting up here. You'll have the formula with you on the test, but it's pretty straightforward. This one, I think the ones I put on test are usually just like E or maybe ln, ln, sine or cosine. That's the usual suspects. So you just keep taking subsequent derivatives, and we're centered at 0. We're going to put 0 in there every time. And those are the coefficients, and follow the formula. And remember, you have these factorials you have to divide by. This was a 3rd degree. I think this is pretty straightforward. Notice when I'm taking the derivatives, like I said, I didn't really put these on a test, but I'm writing the ones there to indicate the chain rule, the derivative of the inside, just to let you know that I didn't forget to do that. So that's all. So this should be pretty straightforward. And of course, you can use your calculator and simplify all these terms. So it's kind of blurry there, but it looks like it's answer A, I guess. I guess it's this. That shouldn't be too bad. Let's take a look at 41's another Taylor. Third degree. There's a fourth degree coming up. So derivatives of e to the 2x plus 3x. The first derivative would be 2e to the 2x plus 3. Then the 3 will go away. And you'll just keep multiplying by 2. So it'll be 4e to the 2x. And then 8e to the 2x. And we have then, so the first f of 0, we plug it in there, will be 1. Then you have f prime of 0 is 5 times x. Then you have f double prime of 0, which is 4 times x squared over 2 factorial. Then you have the third derivative at 0, which is 8 times x cubed over 3 factorial, and simplify it from there. It looks like it's answer D. Okie doke. Number 41. Fourth degree polynomial ln of x centered at x equals 1. So that means you're going to have a bunch of x minus 1s here, which of course, you know, if this, or you're not going to have to multiply those out, obviously. No way. They'll all just sit like this. They'll all be like x minus 1s, x minus first, squared, third, fourth. So you got to take 4 derivatives here because it's fourth degree. So it's 1 over x, and then negative 1 over x squared. Obviously don't use the quotient rule, just use x to the negative 1 here, and then take it and make it and be negative x to the negative 2, and then 2x to the negative 3, and then negative 6x to the negative 4. I just dropped the exponents down just because I wanted to. I didn't have to. Plug in 1, we'll get 1 for the first one. Second derivative, you'll get negative 1. You'll get 2 for the third derivative, and you'll get negative 6 for the fourth derivative. And f of 1 will be 0 because ln of 1 is 0, so we don't have a first constant term there. 1 times x minus 1, then you have negative here, negative 1, so it makes it subtraction right there. X minus 1 squared over 2 factorial, plus the second derivative at 1, which is 2. X minus 1 cubed over 3 factorial, and then minus 6. X minus 1 fourth over 4 factorial. And then you can kind of simplify those fractions. They work out being 1/2, 1/3, and you have a couple of negative terms. Okay, so not too bad. Let's see. All right, now we're getting into the power series. Okay. Power series are series that now have x's in your series, and everything's not just n's. Now you have x's and n's. And to approach a power series, it's the same test every time, thank goodness. You don't have to look at this and go, how do I think about, are there a bunch of different ways I have to start this problem? No, it's always the ratio test. You just jump right in with the ratio test. So this one's actually easy, 2x over 3 to the n. So you just have, so 2x plus 3 to the n plus 1 over 2x plus 3 to the n. That just leaves you 2x over 3. So you saw it whenever, so when the n's are gone, that means you're going to have an interval that's not infinity to infinity. I'll just kind of say these verbally, but I'll point it out whenever you come along. There's 3 things that can happen. There's this case where there's no n's left after you perform the ratio test. That means you'll have a numerical interval of convergence. Another case is if you have x on top and n on bottom, that means your limit will go to 0 because as n goes to infinity, no matter what x is, n's going to infinity. So that's going to go to 0, means you would have convergence automatically for the ratio test. So it's all real numbers. And then the other case is when you have x's times n's left. That means you're only going to have convergence at whatever makes the x value 0. That also means your radius of convergence will be 0. So here we take 2x over 3 and put it between -1 and 1. And solve it, and you get the interval between -3/2, +3/2. And the radius of convergence would be, like I showed right here, there's several ways you can come up with it, but if you just take the difference between the two endpoints and divide by 2, that would work. Because essentially the radius of convergence is the distance from the center, in this case, which is 0, and to either end. But you can just subtract the two ends, divide by 2, that'll get it. One thing I'll mention here that I did the next one, I don't know why I didn't do it for this problem, but oh, I see why I didn't do it, because it was only asking for the radius. It wasn't asking for the interval. But since we have it there, I'm going to go ahead and mention, because we'll do that next problem, is you got to be aware of this on exam purposes. Exam that you have to test the endpoints, because that doesn't mean this interval is your final answer, because it could not converge at either end, converge at both, or converge only at one end. So this one, if I put -3/2 in there for x, I'll get -3 over 3. I get -1 to the end. That diverges. Put in 3/2, I get 1 over n. That diverges. So in this case, that would be an open interval. This actually would be the answer with that interval. There would be no endpoint convergence. Well, whenever a problem's asking for that, you have to test it. The next one, basically it's x minus 1 to the n over 3 to the n. So I'm doing a ratio test where I have n plus 1 over n plus 1. Multiply it by the reciprocal of the original. Flip it over. And I get x minus 1 over 3. So I have no x's left. That means, no n's left. Excuse me. No n's. So we will have an interval. So you take x minus 1 over 3, put it between -1 and 1, because that's where the ratio test converges, is between -1 and 1. Multiply by 3, then add 1 to all three parts. So you're between -2 and 4. Now we have to check for endpoint convergence. So you put in -2, put in 4. This one kind of works a lot like the last one. Don't assume they always do this, because you absolutely will have problems that have converging at either one end or both. But this one, when you plug the numbers in, you're going to easily get two diverging series. All right, so it would be between -2 and 4, open interval. 45, we have x plus 4 to the n over n times 2 to the n. So do the ratio test. So you have x plus 4 to the n plus 1 over n plus 1, 2 to the n plus 1. Then you take the original one series and flip it over. So we have n times 2 to the n over x plus 4 to the n. So the 2's will simplify to where they leave a 2 on bottom. And this n over n plus 1, as I explained earlier, algebraically they don't cancel, but the limit of n over n plus 1 would go to 1. That's the key. It's the limit, not the actual algebraic cancellation. So that does go to 1. So if you thought I made an algebra mistake there or something, I did not. And you'll be left with an x plus 4 on top. So we have x plus 4 over 2. And so we put it between -1 and 1. And we have -2 to 2. If we multiply by 2, have x plus 4, subtract 4 from both sides. And you have the interval of -6 to -2. Now we have to check for endpoints. So if you put in -6 to the original series here, you're going to get -2 to the n over 2 to the n, which actually is the same thing as -1 to the n all over n. That would converge by the alternating series test. We don't care about absolute convergence, just whether or not it converges, but it would converge. But when you put negative 2 in here, negative 2 in the original one, you'll get 2 to the n over 2 to the n, which is just 1. 1 to the n is just 1. Negative 1 to the n is obviously different because you have some terms negative, some are positive. So you end up with 1 over n, but 1 over n by itself is a diverging p-series. So this one's kind of interesting. So you actually, it converges at the left endpoint of negative 6, but not the right endpoint. So you see the negative 6 has the bracket on it, but the negative 2 does not. Okay. Take a look at the next one. 2 to the x, 46, 2 to the x, 2x to the n over 3n factorial. So you place n with n plus 1, flip over the original. You'll be left with a 2x on top, and then 3n plus 3, 3n plus 2, 3n plus 1, and then the 3n factorials would have canceled. All right, you have x on top, you have n's on bottom. That means that limit's going to go to 0. And if it goes to 0, you have convergence for all x. You don't have to solve for anything. When it converges for all x, that means your interval of convergence is negative infinity to infinity, which also means that's your radius of convergence is infinity. In fact, let me mention that for this last problem we did. The radius of convergence would be 2 for this problem. If you took negative 2 minus a minus 6, you get 4. 4 divided by 2 would be 2. So R would have been 2 for number 45. For 46, it's infinity. So let's take a look at, check. So we didn't finish this. So I got 2. Yeah, I did that one. I did. No, I'm talking about the next one. So replace n, then plus 1, same kind of thing right down here. N and n plus 1 will cancel by limit rules. You'll have a 2 left here and an x plus 4 left here. So you have 2 times x plus 4. Put it between negative 1 and 1 and solve. So you divide by 2 to make it halves, and then subtract 4 from everywhere. So you have negative 9 halves to negative 7 halves. And this is very similar to that other one, recent one, where you end up with negative 1 over to the n over n, or just 1 over n. So you get converging by AST for the left endpoint, and you have diverging for the right endpoint. So it would be bracket at negative 9 halves, parentheses at negative 7 halves. All right, number 48. N factorial. This one's the radius of convergence. But this will be a good one because we'll also see a single point convergence. And all right, so we now this one, because the original problem here is not a fraction already. So I just put in n plus 1 and then just divide it by the original. I didn't put this over 1 and then 1 over that and combine them. I just put the n plus 1 term over the nth term. So with that being said, what do we have? We'll be left with n plus 1 times x minus 3. So we saw the case for infinity a minute ago when the n's are left on bottom, but this is the one earlier where I mentioned the 3 rules, and this is the third rule we haven't seen. Anytime you have the n times the x, the answer is going to, this has to converge. That's one thing about power series. It's not whether or not they converge or diverge. It's always going to be, at a minimum, they'll converge at one number. So this one, the only way for this, because with n going to infinity, the only way for this to converge is whatever makes x minus 3 equal 0. Because that way you have 0 times something will be 0, and that guarantees convergence by the ratio test. Any other number for x, it'll just blow up. The limit will go to infinity. So for x minus 3, that means x equals 3 would be where it converges. And anytime that you have single point convergence like this, is the radius of convergence is always 0. Yeah, there's no, like, from 3 to 3, basically, so there's no distance between them. All right, so these next ones are from the representations of functions as power series. We're going to use this ratio, the expression right here, 1 over 1 minus x, that's the geometric series formula. So somehow I want to get x, or get it into the form of what this would represent using the geometric. So this one's not too bad. All you have to do for this one is, you see it's written like this, that's your r is x plus 9 over 7. So we do 1 over 1 minus x, which is r, same thing. So you just put the x plus 9 over 7 in there. Get a common denominator. 7 over 7. You get negative x minus 2 over 7. You flip it over, and you have 7 over negative x minus 2. I went ahead and factored out a negative just so it would match the answer. So it's negative 7 times x plus 2. So that power series, x plus 9 over 7 to the n, would equal this. It's the same thing as negative 7 over x plus 2. All right, let's take a look at the next one. We're trying to see what x minus 10 to the n equals, the function that's represented by that power series. So we, now this one, yeah, they tried to trick us a little bit here. They're starting it at 1 instead of 0. So what we have to do is we have to do like we did earlier with that other geometric series that was just, for numbers only. But the same principle applies here even with this x minus 10. So you put it as 1 over 1 minus r, which is 1 over 1 minus x minus 10, and you subtract off the 0th term, which would just be 1. So 1 over 1 minus x minus 10 is the same thing as negative x plus 11. 1 minus 10 will be 11. So I just rewrote this x minus 10 to the 0 as 1, got a common denominator. So it's negative x plus 11 over negative x plus 11. You subtract, you'll get x minus 10 over the negative of x plus 11. So at this point, see, that's a correct answer, but in order to make it match the answer choices, is I had to pull a negative from the denominator. To pull it, I just pulled it to the outside, and that left x minus 11 on bottom. So that would be the answer, to make it match that answer. I mean, my first answer here is technically correct, but I just pulled the negative out of there to match the answer on the key. And number 51, expand 4 plus 4x squared into a power series by any method. Okay. Find the interval of convergence of the series. So now I'm using, because I want 1 plus x here. So that would be the same thing as 1 minus a minus x. So I'm kind of working with this thing right here. I'm just modifying it. I'm just taking x and make it negative x. That way it gives me 1 plus x. So I have negative x to the n, which you can break down. So now it's just a negative series here. It's negative 1 x to the 1. Now I replace x with x squared right here. So I replace it on the left side and I replace it on the right side. And then I come up with this thing right here, negative 1 to the n x to the 2n. So then I replace, in that expression, this is a little tricky here to see this. I probably won't have anything this challenging on a test, but let's see. There might have been a different way to go about this, but this is what I chose to do. I replaced x with x plus 2. Or I guess I could have multiplied top and bottom by 4 and then figured it out. Well, Yeah, that's okay. Well, let's work with what I have here. X over 2 squared, x squared plus 4, then you multiply by 4 over 4, and then it fits, because it fits what I'm looking for here, because ultimately I'm trying to obviously get to this, but that might have been confused. You know, the 1 over 1 plus x squared, I should have just gone 4 over 4 maybe right there, and then dealt with the x squared divided by 4. I could have worked backwards. I could have gone x squared over 4 equals x over 2 squared. So I should have gone left to right, or right to left here instead of left to right. And we have, so I take the series I have right over here, and now replace x with x plus 2 to get this, which then would equal this. And then we just take the x over 2. It doesn't matter that's raised to the 2n. That doesn't matter. It's still the same interval. You just take the x over 2. You don't have to worry about the 2n part. You still put it between -1 and 1. So it ends up being between -2 and 2. Yeah, that, if you're wondering what happened to square, that doesn't matter. It'll still converge either way. So, all right, so that's the end.